So we were last time in the middle of talking about and I want to kind of get back to where we were, um, the finite square well, the idea that we have a potential like this, where this height is V naught. Yep, Isa just texted me. We're trying to get her back in. Oh, yes, Danielle, thank you. Thank you. I'm sorry, I was worried about too many things. I have like three classes to do that are back to back, and this one is not quite mine, so I'm kind of scrambling. Bear with me. Ah, good. She's able to get back in. So you all can see now, right? You should be able to. Welcome back, Isa. So it turns out the button for like mute somebody's mic, because there was a bunch of background noise, it was using your laptop mic rather than the headset mic, and the button for kick somebody are right next to each other. And you muted yourself right as I was clicking mute, and it meant that like the button that I was about to click jumped.
Okay, I moved to a different part of the house.
Yeah, oh, this is much quieter now, Isa. Oh, she's getting back in. Anywho, um, uh, for the finite well, this potential is V naught, and we're imagining particles with stationary states less than V naught. With energies less than V naught. Um, and those states will be oscillatory in the middle, but decaying exponentials in the outside. We talked about this last time. So this may look something like that. What we saw before, and again, I'm going to write down just, you should have this in the notes from last time. Um, if you weren't taking notes, it's in the video. But what we saw is that we broke this into regions 1, 2, and 3. And that we saw in regions 1 and 3, the particle behaves with an exponentially growing or decaying wave function. So we saw that psi of 1 is A e to the I kappa x. In the middle, this thing could go either way. Well, let's do this here. We could have a term here, be to the minus I kappa x, but, whoops, no I. That's right. These are the exponentially growing and decaying ones. And we know those aren't present because the wave function has to go to 0 at negative infinity. Likewise, in region 2, psi is ce to the ikx plus de to the minus ikx. And psi 3 was, again, we're not going to use E here because that means energy, Fe to the minus ikx. And there's another term that gets crossed out. So now we've got 4 equations and 5, we have 5 unknowns. These aren't constraints. These are, what our wave function is. So we have now 5 unknowns. The constants A, C, D, and F. and the allowed energies. But we have constraints. Those constraints are that psi must be continuous at x equals 0 and x equals L, and its derivative. So that gives us 4 constraints. And then finally, we have the normalization constraint that the total probability must be 1. So for region 3, yes, you're right, it's kappa, Daniel, thank you, because that's the exponentially decaying one. And I should write down what kappa is, where k is the real energy, the positive kinetic energy region, and kappa is this imaginary wave number. Now, when you solve this, I'm not going to go through, I don't know if Jack was planning on doing all this algebra to solve this, but you wind up here with 5 equations and 5 unknowns. I'll say 5 constraints. 5 unknowns. I'm not going to do the algebra. Yes, so Yanju, so in region 1 and 3, you get exponentially growing and decaying behavior. So in regions 1 and 3, that's where we discussed where the kinetic energy is negative, the wave number is imaginary. And what I did was I said, okay, just so we can like at a glance see if something is growing or decaying, we said let's define kappa as this positive definite imaginary part of k, where k is square root, like, because our normal definition of k, if you remember, k was square root of 2m e minus v of x over h bar, right? But this means that this wave number is imaginary, and I made a mistake. Like when I wrote this up here as a k here, it got very hard to see, okay, is this exponentially growing or decaying? So we've defined this quantity kappa, where we kind of put in here, this is the negative kinetic energy, just to redefine that to make it simpler to see what's going on. Does that make sense? Okay. So I'm not going to do the algebra here, but you can do it. You wind up with constraints on what those are, and you wind up with an equation actually that has no analytical solution that you can solve for the energies, but it's in your book. The next system I want to talk about, and I'll talk about it only briefly here, but this is important because it's in your homework, is this one. To your notes, the K and the kappa are the same. Did I use different letters for the constants, Yanju? Because I may have like, I mean, what I probably did, what I likely did in region 3 when I wrote it before was said, okay, F will be this one. Yeah. But this term here is the one that we know has to go away. Because we know it's got to exponentially decay as we go to the right. So most likely that's what you had in your notes. Yeah, so I've named the letters something different here. E to the, I mean, the notation, ah, like I'm kind of getting frazzled here just because I'm trying to get through this as quickly as possible to get to the fun stuff. But I should be more careful. Yeah, the one that's positive here is the one that goes away. It doesn't really matter, which term you call what. But yeah, the point is that here the ones with kappa in regions 1 and 3, there's no I in the exponent because those are growing and decaying exponentials rather than oscillatory things. So I don't think there are any questions about that in the book. This topic, though, there are questions in your homework, so I want to get to these. Here, um, uh, the potential V of x I'll write as 1 half k x squared. So this is like a mass spring system. And in this case, um, it's also like the algebra here is more complex than we want to do. But this also has a set of stationary states. And there are a lot of systems in nature that behave like this. So just to draw a few examples, here is the ground state. Oops. The next state looks like this. The next state has, one more wiggle. So that's up and then over. Up and then over. And so on. So this is, it's analogous to a mass spring system, but it's any system where the potential is quadratic. This is called a simple harmonic oscillator. And the thing that you need to know here, the wave functions are actually complicated. Psi of x shown above. But the energies are very simple. And this is what you need for your homework. Um, the nth energy level, well, I'll write it this way. The allowed energies are n plus a half times h bar omega, where omega is the square root of k over m. Um, well, where k here, if k is the spring constant, um, actually, I'm not going to say spring constant here. I'm going to revise my notation. Or actually, yeah, here's what we'll do. Or the way that it's usually thought about. Yes, n is the number of the state. Um, that's another way that it's often written. Let me make sure I've gotten my h bars right here. I'm sorry, I'm a little bit discombobulated today. I'm coming straight from Physics 211. There's just not enough time to get everything in order. Stand by for just like 30 seconds. I want to check something in the notes that Jack gave me a few weeks ago. It's like, what exactly did he want me to do? How did he define this? I want to use the same notation that he did. He actually doesn't go into that. Okay, we'll just erase this then. Yeah, I want to make sure that I'm teaching the things that he wants. Where here, omega is square root k over m. So why is this useful? Um, this lets us, anytime you have a potential like this, understand its physics very simply. So this means anytime you have a quadratic potential, the allowed energies are evenly spaced. So we've got the first one is 1/2 h bar omega. The second one is 3/2 h bar omega. The next one, it's the third one, but I'm referring to it as E2 as 5/2 h bar omega, and so on. Now, that's relevant to your homework because if you remember way back when we talked about molecules and the forces between molecules, we saw that the potential as a function of distance goes like this. I'm going to zoom in on this to make sure I get my drawing clear. Um, so this is V of R. It has an asymptote here. It goes down and then up. And this minimum here, right, this is the most likely distance between the atoms in the molecule, right? But you might say, well, gee, the region surrounding this equilibrium distance looks an awful like this, right? So this is v of x, and all of those colors are the various stationary states. Let me label that. I'm sorry I didn't post the notes from Tuesday. I do have the video. Everything was just insane with 211 taking an exam. So what you can do is you say, gee, well, this region looks a lot like a simple harmonic oscillator where psi looks like um, psi of x equals some constant plus 1 half kx squared, right? So what you're doing for homework, the approach to that problem is if you want to understand the vibrational states of a molecule, then you Taylor expand the potential around the minimum and keep terms up to second order. And that will give you a potential that doesn't just look visually like a parabola, it actually is a parabola. And then you can approximate the potential here as some parabola, right? And then solve for its stationary states, and that will tell you about the vibrational modes of, um, of a molecule. So Isa, does that answer your question? Yes, Caitlin, I will send this out. Isa, does that answer your question about like how to do this one on the homework?
Are we talking about 30 or
54.
54?
54.
I'm sure I could get somewhere with that.
Okay. I mean, the thing that you need really, like the simple harmonic oscillator thing, it's a big setup, but the main idea is
Mm.
you need that formula
Okay.
here.
Okay. All right. I will.
Uh,
I will do that.
for the other problem that you wanted to talk about, that's one where you're looking at the infinite square well, right? The thing that's like standing waves on a violin string, except instead of going from 0 to L, where the stationary states were sine n pi x over L, now you're just like redefining your coordinate system. So you know that if you have an infinite square well, let's talk about that problem briefly. Um, if you have your infinite well, like so, the allowed vibrational modes, the stationary states, are, whoop, not that. That's not quite right. They're this one for n equals 1, right? They're that one for n equals 2. Remember when we did all this, Isa?
Yes.
So this you know how to do. Or rather, you've seen it. Oh, that's supposed to be a maximum. Whatever. I don't need to draw it out. But you know how this goes. And we did it with a particular coordinate system. We did it where we chose the coordinate system like this and said that this was x equals 0, right?
Okay.
Where psi of x was a sine n pi x over L. We argued that they've all got to be sine because cosine is 1 at the origin, and all of these have to go to 0 at the origin, right?
Mm-hmm.
But your homework is kind of a, let's make sure they understand this. Because what the homework asks you to do is to do it again with a coordinate system like this, where this is x equals 0. And here you'll observe that the blue one is a cosine, but the pink one is a sine. And it asks you to kind of repeat the process of thinking through what the wave functions for the stationary states are, but just with a different coordinate system. That's all that's going on.
Okay. That makes sense.
Any other questions about the homework? Because I know a lot of people want to talk about nuclear reactors and bombs and stuff. Okay, so this next thing is going to be like special topics fun, right? We're going to talk about nuclear physics, and anything you all want to talk about, I am happy to talk about. So what I figured I'd do is start off by introducing kind of basics of nuclear physics, and then pivot to both kind of the story of how some of this was discovered and how it's used in engineering to make nuclear reactors and nuclear bombs and nuclear medicine tests and potential fusion reactors and stuff like that. Does that sound good to everybody? Okay. Issa has given me a smiley face. And please feel free to like type stuff to me in chat. So let's start from some basic stuff. So atoms are made of three pieces, right? So big blue blob is a proton. A big red blob is a neutron, and a little green thing is an electron. That's the notation I'm going to use throughout. And some stuff to know about atoms is that the number of electrons determines their chemistry and thus their the name of the element. The number of electrons matches the number of protons. So the chemical properties are set by the number of protons because that equals the number of electrons. But the nuclear properties depend on both neutrons and protons. So, for instance, this is hydrogen. Where I've got one neutron or one proton and one electron. But this is also hydrogen. If I take a proton, I stick it to a neutron. Works better with the fat coloring tool. Whoops, neutrons are blue. Nah, I got the colors wrong. You know I'm getting, yeah. That's important. We can do this. So there's a proton. Here's a proton. Here's a neutron. And an electron going around it. This is also hydrogen. So these are called isotopes. Yes, there is a course offered in nuclear physics, but it's not offered enough. I wish it were offered more. I would love to teach it. I apologize, I haven't really gotten ready for today. I'm kind of winging this just because I've been so harried with Physics 211 lately. So these are called isotopes. An isotope is a um, different nucleus, a different nuclear form of the same element. So an isotope is a different form of the same element with a different number of neutrons. Because remember, if we change the number of protons, it becomes a different element entirely. It has different chemistry. So different isotopes have the same chemical properties but different nuclear properties. The way that we name these is with another number. So this one here we would call hydrogen 1, which is written like this. And this one here we would call hydrogen 2 because it's got two total things in its nucleus. So that number is the total number of protons and neutrons. So now you know how to name nuclei. So first, some history. In the late 1800s, it was discovered that some substance traveling off of uranium exposed film. So this was the first nuclear radiation. And then, as the years passed, a couple other things were figured out. So the next things to be discovered in order were that there are three types. Oops. Of this radiation, which they called alpha, beta, and gamma. We'll talk about what those are in a minute. And that elements emitting alpha or beta radiation change into others. So the history and the way people used to talk about it is very complicated. But it turns out that now we understand it very simply. Atomic nuclei are made out of protons plus neutrons, right? So these two sorts of decays, alpha decay means a nucleus spits out a helium-4 nucleus. It's helium-4 because helium-4 is a very stable unit. 2 protons plus 2 neutrons. And beta decay is a neutron changes into a proton, or the other way around, or a proton changes into a neutron. So, and here I should say, in beta decay, this also spits out an electron. So some elements are radioactive, some isotopes, I should say. So, and I'm not going to talk about gamma decay. It's not really relevant to this. Gamma decay actually doesn't play much of a role in our story until we get to Danielle's question about medical physics, where it will play a role. Because Danielle, I know you asked for some medical physics stuff last time. Um, so here the nucleus spits out light, which is a gamma ray, but it does not change composition. So what was known also is that all of these radioactive elements, so elements that undergo these kinds of decays and change into others, they are unstable. They do this over some time. And I'm going to, let's see if I can make this work. I'm going to grab a graph. This is a super famous chart. This is the periodic table not of chemical elements, but of isotopes. So if I zoom in on this, it's kind of hard to see. There are lots and lots and lots and lots and lots of entries. And I am what you can take away from this is, well, I should tell you what the axes are first. So let me make sure I've got this right. Sorry, I've been teaching like other classes. Um, I don't know the color legend here. Yeah, yeah, this is right. So this axis here is the number of protons, which tells you what chemical element it is. This axis here tells you the number of neutrons, which tells you which isotope of that chemical element that it is. And if you look down at the bottom left, you'll notice, let me zoom in as much as this will let me, you'll notice there are two black squares right next to each other. Right? So the way you read this is that these two black squares are the two isotopes of hydrogen. These two here are helium. So what this tells us is that hydrogen has an isotope with one proton and no neutrons, and an isotope with one proton and one neutron. Helium has two protons and one neutrons, just because it's helium, and then this one that I'm drawing the arrow to right now in green, that one is two protons plus two neutrons. The colors are interesting. So black is stable. Blue, which conflicts with this color, or pink is beta decay, and yellow is alpha decay. Our story is not actually going to take us that much into decay modes, though. All we need to remember is that many elements, or many isotopes are radioactive and will change into others. The other colors mean other things. It turns out the purple ones will be interesting to us later. But notice that above this line, none of the elements are stable. Green, so gamma decay, remember, doesn't change the composition of the nucleus. Green is actually, it fissions on its own, is spontaneous fission. Um, so now let's talk more about what we see on Earth. So anything that is unstable, you would think, well, it has decayed. Since then, you're not going to find a radioactive element lying around on Earth because it was, even if it was there in the early Earth, it would have gone away by now. But there are some radioactive elements, some radioactive isotopes that have half-lives that are so long that we still find them around. So those are, so now we start talking about uranium. It's got two isotopes which have very long half-lives. Uranium-238, and we're gonna make a table of their properties. Um, its half-life is around 4 billion years. And uranium-235 decays much faster. Its half-life is around 1 billion years. So that means that this is only a small fraction of natural uranium. And remember, you can't use chemistry to separate the two because they have the same chemistry. They're both uranium. Yes, this is exactly why the game Half-Life uses the lambda symbol. In my first semester here, I've got so many memes from students about being Dr. Freeman. They were like making Gordon Freeman memes about me. It was kind of funny. Um, so here are the two isotopes of uranium. It was discovered by Marie Curie and people who kind of followed after her that the things that uranium decays into are also radioactive. Yeah, Half-Life 2 is and all of Half-Life is a game about some like, ordinary business-minding physicist who has to save the game from aliens. But Half-Life 2 was the first game that had a real physics engine. So there are tons of physics puzzles involving mechanics, levers and balancing things and so on that you have to use. So Half-Life 2 was a super classic, like back when I was in undergrad. It's worth playing. Um, so where were we? So Marie Curie discovered that the things that uranium decays into are itself radioactive, and this is actually pretty common, right? When you have a radioactive thing that decays, if it's got a long half-life, often the thing that it decays to will have a much shorter half-life, and there'll be a bunch of decays in sequence until you finally get to something stable. And people did some more work. And then in the 1930s, everyone was quite familiar with this. They were familiar with the idea of radioactive thing decays, a little piece comes off, and it produces a smaller atom, slightly smaller nucleus. Remember, radioactive decay, our options are either we spit out 2 protons and 2 neutrons. So spitting out 2 protons and 2 neutrons just would move us just a very tiny little bit down and to the left on this chart, right? So like, you know, this thing would move there. This thing would move there. this thing would move there, which would move there, which would move there. Or things that undergo beta decay, a proton changes into a neutron, or vice versa. You move diagonally the other way on the chart. But in the 1930s, there were two radiochemists, actually three. Um, I have their, get you their pictures. So this guy, Frisch, Otto Frisch, um, no, excuse me, Hans Frisch, I think. This guy is Otto Hahn, and Strassmann, I believe, was the third. I don't have his picture. Were doing something unusual. They were playing around with these radioactive elements, and they noticed something very strange. They noticed much lighter elements appearing. So we were in the position of heavy element goes to other heavy element to slightly lighter element. That we understand well. But heavy element goes to thing half the size. Again, only tiny fractions of the elements present were doing this. What happened, right? That's not a known decay. And then, so these two folks, who were both refugees from Nazi Germany, wrote to Lise Meitner, who saw their chemical results, and said, oh, well, you've taken a heavy atom, and now your chemistry is producing two other atoms that are much lighter. Well, you've split the atom. So this was the discovery of nuclear fission. And this is the super exciting thing that we will talk about for the rest of this. So, how does nuclear fission work? Nuclear fission, the uranium atom splits into two pieces around half of the size each, although there's some variation. It also spits out two or three, this is the big deal, free neutrons. So now that we are talking about neutrons, what happened? The other really important piece of understanding nuclear reactions is, and this is the big question, is what happens when a neutron hits another nucleus? And there are a couple of choices. The first one is it bounces off and loses energy. If it's going fast. That's one option. The second option is it's absorbed into the nucleus that it hits. And if that was it, then this would be the end of our story. We could use neutrons to change elements into other elements, right? This is the great dream of the alchemists. They wanted to change lead into gold, and it turns out throwing neutrons at something does that, right? If I want to transmute, say, um, nitrogen into oxygen, nitrogen has um, 7 protons, oxygen has 8 protons. If I keep throwing protons at a nitrogen, excuse me, if I keep throwing neutrons at a nitrogen nucleus, some of them will stick, and then by the process of beta decay, some of them will turn into protons, because I'll make unstable things, and I'll make oxygen. So if this was it, we could turn elements into other elements. But this third bullet point is the one that changed history. For very special uh, nuclei, they induce fission. So you probably all have heard the term chain reaction, right? Whenever a fission happens, I get 2 or 3 free neutrons out. And those free neutrons can then go find other nuclei and fission them. So this is how you make a nuclear chain reaction. So now we need to talk about, in more detail, the 2 isotopes of uranium. So uranium-238 and uranium-235. Uranium-238 is 99.6%. And please ask me questions, by the way. I'm just kind of rambling here. But if you have questions or comments about this, or some of this is what you already know and you want me to go faster, let me know. Uranium-238 doesn't fission readily. There's a small chance for very fast neutrons. And its behavior when it's struck by a neutron I shouldn't say usually, I should say often. And changes to uranium 239, which decays rapidly to plutonium 239. You probably also know that plutonium is special. Uranium 235 is only 4% of natural uranium. It fissions often when struck by neutrons. It fissions very often when struck by slow neutrons. So, yes, so So you guys gotten right to the point, right? Uranium-235 is the thing that I can sustain a nuclear chain reaction in. So this can sustain a nuclear chain reaction. The trouble is that the only difference between uranium-235 and uranium-238 is that uranium-235 weighs, the atoms have about 1% less mass. So you have to have some way of sorting atoms by mass. The original technique used for it was gaseous diffusion. Um, Atoms of different masses diffuse through membranes at slightly different rates. Um, so they just turned uranium into a gas by making uranium hexafluoride, UF6, which is, it's just a molecule you can make out of uranium that's a gas at room temperature, and they'd pass it through membranes and very slowly over time sort them. And that's how we got the uranium to make the bomb that destroyed Hiroshima. The modern method is by using centrifuges, by using the gas pressure in an ultracentrifuge to force the uranium 235 to the outside, and the uranium 235 goes more to the inside. And that's the thing that there's so much controversy about Iran trying to use lots of. Where do we find uranium? It's all over the place. It's a common element in Earth's crust. You can mine the stuff. Um, it's not terribly radioactive, right? Remember, it's got a half-life of billions of years. That's the only reason why we can still find it. Um, so yeah, uranium can be mined all over the world. There are lots of different places. Um, yes, there is a lot in Canada. I think there's some in Colorado. I believe there is a lot in Central Africa. It's not hard to get. But the yes, I have one, Matthew. I have a little saucer. That's so uranium. Its chemical properties and its nuclear properties are totally separate, right? Its chemical properties happen to be that you can make some really pretty orange glaze out of it. Yeah, Isa. I mean, like, and that is legal. There are no regulations on ownership of like natural uranium. You can own uranium ore. There's nothing wrong with that. So this was figured out around 1940. This idea that you could sustain a nuclear chain reaction. And a couple of people figured this out, and they also figured this out in the context of World War II. And they wrote a letter to Roosevelt and convinced Einstein to sign it that said two things. One is that it might be possible to make a sustained nuclear chain reaction that makes a lot of energy. And the other is you might be able to make bombs. So let's talk about the. We've got 14 minutes left. I actually may continue this into next Tuesday if you all are super interested in it. We can just put the Schrodinger equation up on a shelf for a little while. Is the if you'd like to do that, Isa, then that's cool. Like, please give me feedback. I'm just kind of like guessing what you all find interesting here. So, if you want to make a sustaining nuclear reaction, then what do you need to make a nuclear reactor? Let's talk about this. Um, Actually, let's talk about bombs first. You need enough uranium-235 in one place So this is Jack's. Great question, Grant. What about plutonium? Um, I'm going to mention the University of Chicago thing, building a nuclear reactor at a weekend in about 3 minutes. Um, Uncontaminated by much uranium 238, since uranium 238 absorbs neutrons. Um, what you need is every time a fission happens, an average of 2.4 neutrons on average if at least one of these causes another fission, then the reaction grows exponentially. And in a bomb, um, you know, this thing grows exponentially until it blows itself apart. Um, yeah, so let's get all the questions. So the thing about plutonium, so here's the trick, or plutonium 239, which has very similar properties. That's why plutonium is exciting. So what are these other things? What about fusion or H bombs? So nuclear fusion I have not talked about yet, but it turns out that if you take very light atoms, we'll just stick this picture here. Here is a plot of, and I doodled this plot before, I like sketched it for you, but now I have it actually graphed. Isa, I'm going to come back to blowing up Colorado. Um, so this is a graph of it's the inverse of potential energy versus the nucleus size. So going this way is fission. This requires special fissile nuclei like uranium-235 that are rare, but going this way is fusion. And this requires temperatures on the order of 10 million degrees. And the only way we have to make temperatures of 10 million degrees is, you guessed it, with the fission bomb. So to make a nuclear fusion explosion, what you do is you collect together. It turns out the easiest ones to do are these two isotopes of hydrogen. H3 is called tritium. Uh, H2 is called deuterium. The problem is that deuterium is stable. You can harvest it out of, you have deuterium in your body right now. But tritium is radioactive, which means that you've got to produce tritium in a nuclear reactor. It's got a half-life of like 30 years, I think. So in order to make a fusion bomb, a thermonuclear bomb, you have to first build a nuclear reactor that produces lots of neutrons. Remember, inside a chain reaction, there are neutrons flying every which way. And then once you have this self-sustaining nuclear reactor, if it's got water in it, the hydrogen atoms in that water, some of them will absorb neutrons and become deuterium. Some of them will already be deuterium. And then some of those will absorb one more neutron and become tritium. Then you harvest the tritium out of that cooling water for a nuclear reactor, and then put that tritium next to an exploding fusion bomb, an exploding fission bomb. And then there's enough temperature and pressure to induce nuclear fusion. Tige asks, what about lithium-aided ones like the Castle Bravo bomb? It turns out another thing you can do, and this is actually done by almost all nuclear weapons used by major nuclear weapons powers now, that if you have some amount of, so nuclear fusion also produces neutrons. Neutrons don't make nuclear fusion go, but it produces them. So the problem is, um, well, the possibility is that inside an ordinary nuclear bomb, it will tear itself apart very quickly, and it won't fission most of the uranium. But if you take some small amount of fusion fuel, of tritium and deuterium, and also lithium, as Tige points out, but tritium is the thing you really need, um, and you put that inside of a nuclear bomb, fusion doesn't contribute much to the total amount of energy. Right? Fusion doesn't really, it's not a big energy source there, but it is a source of neutrons. And once the fusion reaction starts, the neutrons it produces will fission the rest of the uranium more rapidly before the thing blows itself apart as quickly. That's the secret to miniature nuclear bombs. So you probably know that the nuclear bombs that destroyed Hiroshima and Nagasaki were very large, but now nuclear bombs are small enough that they can be put inside of artillery rounds. That's how it's done. Is there TK asks, can't you find tritium at the bottom of deep bodies of water? Yes, at the bottom of deep bodies of water, there's probably more tritium fractionally, but it's still a tiny, tiny amount because it's unstable. You know, it's got to be produced in reactors. So this is how nuclear bombs work. But now I want to transition to the more exciting thing, nuclear reactors. So there is one other property we have not mentioned. Well, there are two properties we need for nuclear reactors. I'll mention those now. One of the things I'll say about a nuclear bomb is that the time it takes from one fission to produce neutrons to induce the next fission is nanoseconds. So the reaction grows exponentially extremely quickly. But if we're trying to control a chain reaction, I need two more properties. One is that slow neutrons fission uranium-235 better than fast ones, and some small fraction of the 2.4 neutrons per fission actually come from the decay products, are delayed. So this can be like 5 minutes. So instead of coming out of the uranium-235 nucleus themselves, they only come out a few minutes later. And since they only come out a few minutes later, that means we actually have a hope of controlling a nuclear reactor. So what I'd like to do now, we've got 3 minutes left. We will do more nuclear physics next Tuesday. If I'm still teaching, we will do more of this Tuesday because you all seem to be very intrigued by it. I am too. I find it fascinating. And we still have to answer Issa's question about whether or not she could blow up Colorado. So to make a nuclear reactor, you need a block of uranium. And the problem with that is that the fissions from uranium produce fast neutrons. So what I also want in between my two blocks of uranium, I want a substance called a moderator. And the best moderators, this needs to um, not absorb neutrons and slow them down. There are two really good moderators. Um, Graphite is an exceptionally good one. So those of you who watch Chernobyl, um, the whole thing about like finding blocks of graphite everywhere, um, the Soviets wanted to build very cheap, very high power reactors, which meant they wanted to do it mostly with natural uranium. They didn't want to enrich the uranium and increase the U-235 content because that's expensive. So they said, all right, we need, since we're only using the natural fraction of U-235, we need to moderate these neutrons in order to make the thing more reactive. So that's what the blocks of graphite were for. And this is essentially a nuclear reactor. So a fission happens here. Oops. Some neutrons come out. Maybe one of them escapes. One of them goes this way. It bounces around the moderator, and then when it goes to the other side, it is moving slowly enough that it will induce another fission. And these blocks of uranium ping-pong their fission neutrons back and forth, inducing more fissions as they go. Isa asked, weren't the rods in Chernobyl tipped with graphite? Yes. So in order to, and it's 1:50, people who need to leave, can leave. We'll pick this up again next time. But in order to control a nuclear reactor, what you can do is you can also arrange to insert neutron absorbing rods, so rods made out of boron, which absorbs neutrons strongly. There are a few other things between the blocks of uranium, and those will suck up all of the neutrons and slow down the reaction. But the engineers designing the reactor at Chernobyl were lazy. They said, we want to use, in order to control this thing with the fewest number of rods, we want to have the end of the rod be graphite to speed it up, and the middle of the rod to be boron to slow it down. And what that meant is that when you're trying to move the control rods around, especially in a panic situation, there's a small chunk of the reaction that's actually being sped up that's near the graphite tips, and I can show you a drawing of that next time. We can't end, though, without answering Isa's question about blowing up Colorado. It turns out that, and people who need to leave, again, please leave, but I want to answer Isa's question. It turns out that with enough uranium-235, so remember, natural uranium is 0.4% U-235. Natural uranium, you can only make a sustained nuclear chain reaction with a really good moderator, like graphite. The reactor made in Chicago, I think I have a picture. So this was the world's first nuclear reactor. And this is stacks of uranium and graphite blocks that were assembled by high school students over a weekend in the University of Chicago. They hired these high school kids and said, hey, stack all these things up. And it produced like a milliwatt of power. This is a proof of concept. And the more you enrich the uranium fuel, the easier it is to sustain a nuclear reaction. And it turns out that you can sustain a nuclear reaction using water as a moderator if you have enriched uranium. Not at 0.4%, but at more like, I don't know the percentage, but like 2 or 3%. So in Colorado, you cannot blow up Colorado with natural uranium because because you cannot sustain a chain reaction in natural uranium without blocks of graphite to be moderators. You could if you had big blocks of graphite. Like if you mined a bunch of uranium and you stacked up uranium and blocks of graphite, you could build one of these. It wouldn't be an explosion, but it would generate a lot of heat. But remember that the half-life of uranium-235 is a lot shorter. So in past years, not now, but in the past of Earth, there was more uranium-235 around. And you could make a reaction moderated by just like natural uranium ore and water. And this happened in Africa. Down below the ground in Africa in a uranium deposit, there's evidence that there used to be a natural nuclear reactor beneath the soil of Africa in years past when natural uranium contained more U-235. I'm sorry to have run 4 minutes over. People seem to be interested in this. If there are any more questions, I am happy to answer them. Otherwise, we'll pick this up on Tuesday. And I'll try to get some slides together to like make this more organized. I'm sorry, I've been just overwhelmed with too